Hey Peter, how you doing? Sorry, I'm a bit late. Oh, are you there?
Can you hear me?
Yes, I can.
Okay.
How are you doing?
Uh, and there.
Right. Um, I was just looking for my presentation. So I think you weren't on one of the main meetings where I went through the presentation.
Correct.
Um, so I'm not. So let's take a look at. Let's take a look at the presentation, what I put together.
Okay.
Oh, here it is. There you go. All right. Actually, can I just hold on a couple of minutes? I've been running between meetings. I just need a quick break. 2 seconds.
Okay. All right.
Okay, that's better.
I think I did respond to all the invites.
Okay, yeah, no, it's not a problem. Right, let me share. Let me share the screen. Okay. Let me. Can you see that?
Yeah.
So this is actually just for interest. This is the Blackwell. I don't know if you followed the NVIDIA GTC and their announcement of their latest machine.
Oh, this is interesting. Yeah.
Yeah, so this on the side, this is a prototype that they showed the thermal side. So here's the liquids. They have blind mate liquids similar to us, look.
Yes.
So that's their setup there, but they also have fans for air cooling as well. There's a liquid cooling,
Yes.
which is interesting. Um, anyway, so that's that, and then it's 120 kilowatt rack is what they're doing. I talk about the power delivery, which isn't relevant to us, but they've got like 2.5 meters of cable really, or interconnect between the main facility power and the chip power. So there's a lot of potential for losses there, especially when you're pumping 120 kilowatts.
Yeah.
And then I show that they've got rid of motherboards and they're introducing tons of cabling. So this is just a testament to what we're trying to do in OCP HPC is we conned onto the right thing, and they're beginning to catch up with what we identified 3 years ago.
Yeah. I agree with that. They're kind of slow.
Yeah, but hey, so this then just talks about the the Frontier supercomputer and what would it look like if we made it up out of walls of compute. And they say that's about 50,000 GPUs, CPUs, and switches. And if we look, there's our HPCM, so about 50,000 HPCMs is the way we would build Frontier.
Yeah, can you go back one? Can you comment on what the different volume is?
Between the machines, yeah, we're about 70% of the volume of this, the storage,
Okay.
and this is about 5,000 square foot, and we're about 67% of that, if I remember rightly.
Okay.
We may be slightly bigger. We have made the module slightly bigger since I did this. But also energy density, we can run it like 240% more power if you could get it in there in this configuration compared to their 29 megawatts. We could do about 8. This could go if we had 1.5 kilowatts per module or whatever it is. This could be about 70 megawatts.
I see. Okay.
29. So in the same footprint, if that was a desire. But
okay.
it was less. It was more about we could replicate the machine. This is how you could replicate a machine. These aisles would be closer together, and ideally you might have gantry robots servicing the modules in the interconnect.
Okay.
Then we zoom into the HPCM. I basically tell everybody that I've got another presentation to get into the details of the HPCM, but basically it's roughly the size of an EU-sized brick. So I said, all in all, it's just another brick in the wall.
Okay.
If you know the Pink Floyd.
Okay.
So I just talk about what it is, which we all know, obviously. And then I say, but we can be a supercomputer, but this is a ChatGPT generated telecom box in a Lisbon street. And I said, well, we can have a 6x6 of our HPCM modules inside there, for example. And I sort of show that being populated in there. Right. So the same hardware can go from a supercomputer to an edge telecom edge box, or and then I say, well, also we can have a little tiny wall in our homes with maybe 4 module sites, and it can be designed into the HVAC system in the hot water system, so that the heat from it can help heat your hot water or heat your house, depending on the needs.
Yeah.
And again, we can just populate those modules there. So my analogy there is, if you've got a teenage son and he's just got his latest GPU gaming machine, and it's burning almost 1 kilowatt of power, his bedroom's boiling, gets crazy hot compared to the rest of the house.
Yeah.
And this, by doing this, it takes that problem away, and he can still buy his gaming PC, but it's wrapped up in one of these now, and you just plug it in, and every home has it. Now Europe's a bit more organized around this sort of planning in a government level, so this has sort of more chance of saying, one compute module for all situations. I mean, I can see them putting in the rules of when you install a HVAC system, you put a couple of sites in, for if it became a standard, obviously.
Okay.
So now I talk about the power delivery. So I reference the Blackwell 2.5 meters, whereas we're 0.2 of a meter. So I just show in this diagram, the facility power is literally couple of inches away from the chip power, and then we got some routing, so we're 10% less than 10% of the routing of the power, so the copper losses are a lot less, or and it's lower cost because you use less copper,
right?
Or higher efficiency. Now this is where I wanted to chat with you. So you've not seen this before, right?
That's correct.
Yeah, so what I tried to do was put everything together that we've been discussing in a little bit of a circuit diagram.
Yes.
So this piece in the middle is the HPCM module. So first of all, so this is where we do the cooling of the SSDs. So we've got all these channels going between all the all the media and connectors that are interconnected.
Yes.
And that then flows up into our little immersion chamber, and then it comes out and goes back up to the return. We have 8 of them, so this is just showing us this is times 8.
Yes.
Times 8. And then we would have a valve on the inlet with a temperature monitor on the outlet, making sure that depending on what power we're burning in here, we always get a 65 degrees C return temperature. So this valve opens and closes to reduce the flow or increase the flow on the need. And
Yes.
you do that 8 times again.
Yes.
So we've got one control loop going on here 8 times. And then the water comes up to the heat exchanger, and then we've got facility water, which again, we need to control the flow of the facility water through the heat exchanger. So there'll be a certain drop, and I've just done 60 C here, which is then used for energy reuse. And these are just examples. So I don't, so we've got another similar control loop going on the facility water for energy reuse purposes.
Okay.
And then finally, we need to pull this vacuum.
Yes.
And so this is where I've got this liquid ring vacuum pump, where I did a little bit of research on. Sounds like 0.2 bar isn't difficult to pull, and these liquid ring vacuum pumps are pretty good. They can handle fluid as well as gases. They compress the gas. And this is where I'm a little bit unsure, because we probably want like 80% fluid to fill up near the top, so that this is typically sucking air in, but equally we want to make sure we get a flow. So it'll be a mixture of air and water. So I don't know whether this will work, but in researching it with the help of ChatGPT, it seemed to think that the nice thing about liquid ring vacuum pumps is they work where there is liquid in a circulation. So, but again, this is where I don't know. So we do need a control loop on this vacuum pump to see that we're pulling 0.2 bar for the 60 degrees C or 65 C, whatever that is. So
Yes.
I was going to put a sensor on the vacuum on this side to control the speed of the vacuum pump, I guess.
Where's the sensor?
I don't have it in this diagram yet, so but I have to put one in for that.
Okay. Yeah.
So
Okay. I'm also sorry. I'm also unsure of how that liquid ring vacuum pump handles the mixture of fluid and vapor. I've seen warnings about that, that it's difficult to do, and it results in a short lifetime. But I don't know. I don't know much about it.
yeah, and I guess so my point here is this is a cartoon we've come up with. We need experts. This is you've got 3 control loops going on here, right? Well, arguably you've got you've got 8 here, so you've got 10 control loops all working with or against each other. So you've got to have all of this in sympathy. So it's a fairly slow control loop, but the actual power being driven by one of these modules can change in a nanosecond, I guess. But the ability to pull it away is a bit of a slower control loop.
But the thermal time constant is longer, yeah.
Right. So, but I mean, control theory is control theory. Who cares about the speed? Is relative, right?
Yeah.
So that has to be done. There are going to be reliability claims issues about the valves failing or the pump failing, I'm sure. But we've got one of these per column. So if a column did fail, then you're going to lose 8 modules, and so it's not the end of the world, and you can then service that one column. So anyway, so then in the notes, I talk about the vacuum pump. I talk about the 2-phase, the 0.2 bar, and I said 7 times more efficient versus single. And I've just OCP HPC sub-project meeting discussions. So that's with the likes of yourself and Nad and the likes, is where. So I've said, that's my reference point. Then the conformally coated copper is 7 times more power per unit volume of copper. And there's the UIUC link for that. And then water is 4 to 9 times better thermal conductivity than PaO or fluorinate, which are alternatives. Now, what I think I've done wrong is I then said, well, 7 times 7 times 4 is 200 plus improvement. But really, this one is, I can't multiply this. This just means we can use less copper. I guess if we use the same copper, then we could have a 200x improvement, or we use less copper and we don't have as much of an improvement. But my argument is that's a big number and should help us to reasonably cool a kilowatt processor. But then I highlight here unproven hypothetical concept only. So that's that. And
so
then,
hang on, go back.
Yeah.
So your footnote 2, is that relate to your professor at Illinois University?
Yes. The conformal coated copper, that's 7 times more power per unit volume it comes out of that link.
Okay.
If you use the same amount of copper, so am I correct, do you think, multiplying the 7 times for two-phase that you mentioned, the 7 times assuming we use the same amount of copper for UIUC, and the 4 times for using water versus PaO, it comes.
Well,
is that a fair multiplier? Is that not work?
I don't get the second one. I believe the first 7x for water boiling, that relates to the latent heat of vaporization and number. The last number of 4x, I'd have to check. It turns out if you lower the...
Oh, that's from the Boyd paper. So Boyd...
Okay.
Boyd have said that PaO is 4 times less thermally conductive than water, and fluorinate is 9 times less.
Okay. All right. Then the number 2, I'm not understanding that.
So if we actually, let's just link to the paper then. No, hang on a minute. Let's just. Won't let me get at it. Open. This is, well, yeah, this is electronic design. I think the paper is behind the paywall, but this one references it. Let me just do a comment. Yeah, there you go. We demonstrate 740% increase in the power per unit volume. So in our study, we compared our coating to standard heat sinking methods. And this translates to much higher power per unit volume. So I guess it's per unit volume of copper. So you use a big heat sink, right, that you attach to your die, and copper is really conductive, and so it conducts to a big surface area, but there is a thermal resistance there, and then you transfer that heat to the fluid, right? So the way I read it is for 7 times less copper, you would have the same heat transfer with this conformal coating approach.
Yeah, you could be right. It's a bit of a tenuous link, but I think. Yeah,
well, so my thinking on this was actually I should, if you actually, instead of using the same amount of copper as a heat sink with this method, you just use 7 times less copper and have the same thermal performance.
Yes.
And one of the big issues with water, well, actually, I'll come on to that. That's the next slide. I said the water use concerns, right? It's electric. So ideally, we'd want to use water for environmental reasons and because of its energy, its efficiency in taking heat out. First problem is if electrically conductive, and that's where the conformal coating should isolate. Bacterial growth, especially if you've got any stagnant water areas. So can we eliminate the stagnant water areas? Is that actually possible or not? And what about the water temperature? Apparently the temperature of these loops is beautiful for bacterial growth. And maybe if we're at 65C, then we're in better shape to avoid that. But equally, I understand bacteria can grow at very high temperatures as well. It's just a different type of bacteria. So it may not go.
Yes.
Corrosion, material mix issues, is that something we can deal with or get over? And water treatment, we could treat the water, but that will reduce the thermal conductivity and it introduces more sustainability concerns. So that's basically saying, look, ideally we want to use water, but it's not without its challenges. And so that's basically all I've got in the presentation. I don't have I was going to get I'm hoping to have a little 3D simulation of the water flowing through the module so they can actually see that water flowing through the module.
Well, I think you've done a good job of pulling this together, Alan.
Thank you.
Yeah. So UIUC means the University of Illinois?
Yeah, Urbana-Champaign.
Yeah, okay.
Do you have any reference for your 7 times more efficient, or is it just your own experimentation?
You can obtain that by comparing the number of joules of energy to boil a gram of water versus the number of joules of energy to heat the water from 0 degrees C to 100 degrees C.
Right.
So it's a fairly simple calculation.
Is there a sort of an online reference where I can just point straight to it and it says it's
No, that's something that I figured out on my own. I haven't seen a reference to it.
Okay, that's fine. Look, I mean, either we could do a separate sort of backup slide on what you just said, if you could create a slide on that with the information and links to the base information, or I'm happy to just leave it like this. I was discussing with experts in our meetings, and this is a common view that we can get 7 times more efficient versus single phase. I think I'm happy to leave it as it is, basically.
Okay.
Do you agree with the 7 times 7 times 4 though? If we use the same amount of copper volume,
Hang on a second. I just thought of a problem. When you reduce the pressure,
yes,
the latent heat of vaporization changes, and
right.
it changes in a not good way.
Oh, right.
So that you have to modify that, because the 7x comes from latent heat of vaporization for water at atmospheric pressure, and at 65 degrees C, that latent heat is less, and I can't tell you off the top of my head how much less it is.
Okay, is it something you could easily work out in a short period that I can change this number based on what that impact is?
Okay.
Not right now, but if you could do it before I have to, before I got till the 15th and I need to hand in the final.
Okay, okay. If I do that, would you give me a credit at Electronic Innovations?
Electronic Innovations. Yeah, what's that? I don't know what that is.
So with your footnote, you would say you
Oh
would.
yeah. No, absolutely. I didn't really want to call you out. I don't mind putting your name to this if you're happy to do that. Yeah, no, I'd be more than happy to say it came from you in whatever. For yeah, you tell me what you want me to put in the quote
Yeah. Okay. Um.
in the reference.
Yeah. Okay. So this is a tough week for me, but I think I can do that.
Okay. But do you think it's gonna, so that's 7x, is it gonna come back down to 1 or is it gonna come back down to 6 or 5 or something like that?
Maybe 4. I don't know.
Okay. All right. All right.
Yeah.
Okay, well, it'll be what it will be, but yes, thanks for that. And I mean, if you want, if you wanted to put the little explanation in your website of where you get the final figure from, you know, the 7x and then the 4x, if you wanted to do a little short page on that, I can give you that link. I can put the words in for your reference you want, and I can link people straight to your webpage.
Yeah. Unfortunately, I don't have a web person who can do that easily.
All right, okay.
Yeah. But
All right, well, we can link to your website, and then they can find you and ask you specifically.
Yeah. Okay. All right. Yeah.
Okay. Well, that was really all I had to cover. It's like, am I fundamentally screwed up here in this idea, this sort of block diagram, and we've spotted this one, so that's good. Thank you for that. And
Yeah.
let's get that number right. And I can reference you directly.
Okay. All right. Shall we leave it there?
We can leave it there, unless there's anything else you think I should highlight or I'm missing.
No, I think you've covered it.
All right.
Oh, yeah.
Okay. Well,
Yeah.
thank you, Peter.
Yeah.
Thank you for your help and your input on it all. It's good fun.
All right.
Hopefully we'll engender some interest that'll cause maybe more participation.
Yeah.
Alrighty, take it safe.
Thank you.
Bye.
Bye.